Hi, my name is Randy Sturbins, and I'd like to introduce you to the Soundalyzer. The Soundalyzer is a simple little Arduino contraption that measures the amplitude of sound whenever it's turned on. Let's take a look at how it works. So here's the schematic for my project. We have an Arduino, the SD card shield, our microphone, and the 741 op amp. Now, although this LM thermometer is still technically part of the circuit, he doesn't really serve a purpose in this project anymore. Sorry, bud. These two batteries here are only used to give the positive and negative 9 volts to the op amp. The Arduino itself is powered via the wall. Now for the fun stuff. Here we have the obligatory voltage divider with the microphone and the resistor. Whenever the microphone registers sound, its resistance varies, therein creating a signal on that middle lead. This signal, however, has a DC offset, which is why we run it through the capacitor to leave us with just the AC component. Here we have a basic inverting amplifier. The signal comes in here and is outputted here. The amplification is a ratio of the feedback resistor here over the input resistor right here. This output signal gets taken to the analog input on the Arduino. Once the Arduino code processes the signal, it gets outputted into the SD card for storage. Now we'll see what the Arduino does with the signal. Here's our Arduino code. At the top we have the basic setup for how the SD card is initialized. Moving down, we establish some variables, such as integers n and m. These variables are defined as such. T is the number of milliseconds since the Arduino has been powered on. N reads from analog 0, which is where the amplified sound signal is coming from. Now this signal isn't calibrated in any way, but it's still useful to compare each sample's signals against each other. M has been calibrated to read degrees Celsius from the LM thermometer. However, we will not be seeing any of its data in the following analysis. Finally, we have out, which opens a file called data.csv in the SD card to write to. This bit of code prints T, N, and M all comma separated in the data.csv file. Finally, we've got the same print scheme that prints to the serial monitor that I could use while testing. Now let's check it out in action.
The plus is not the charge here, it's this phase, okay? So that means electrons are most likely to be found in between the two atoms, and that...
So the purpose of this project was to measure the amount of sound radiation, you could say, that I am exposed to throughout the day. I took samples several times at home, and at least once in each of my classes. Now since the sound signal isn't calibrated, I need a control to base all the other samples off of. This sample I took at night, while there was very little other noise going on. As you can see, there's this trend at the bottom that can be explained by the subtle sounds that happen all around us that we never really pay attention to. The peaks that you see can be explained by random noises that occur, such as me coughing or neighbors slamming doors. This makes a good ground for us to compare our other data to. Now here's some stark contrast. This was taken in my music class, with 100+ wind instruments blaring right in its face. Unfortunately, the Arduino can't read above 5 volts, so it caps out at that 1023 mark. It's interesting seeing that dip in the data. That's probably when the professor was working with only a certain section and not the entire group. Next, let's check out something a little more familiar, like, how about our lecture? This sample was taken during the presentations. For reference, these two peaks are probably at the ends of their presentations, when everybody was applauding them. It's interesting to see how each of the speakers trail off as they get into their speech. It's like they're really enthusiastic at the beginning, but then it kind of just dies out as they go along. So let's compare how professors present compared to students. Here is a sample from my music lecture class. Now, the room that she's lecturing in is not very large, which means she doesn't really need to speak very loud. In fact, those spikes are probably due to the students making noise rather than the professor. Underneath that, you can see she maintains a moderately quiet projection. Compare this with this. Now here, the professor was in a fairly decently sized room. Not a major lecture hall, but one of the computer labs. So he requires a bit more projection to communicate with everyone in the class. This one is actually pretty interesting because his projection actually goes up as he continues with the lecture. However, his projection is nothing compared to the next sample. As you can see here, this professor maintained a fairly high volume throughout the entire lecture. But it makes sense because this was a presentation in the big lecture hall on the ground floor of Baker. And as with the previous two professors, you can see that there is no diminution in her volume throughout the entire 30 minutes that I took this sample. And just for fun, here are a couple samples from home. Nothing really interesting to note. Well, that's about it. I hope you've enjoyed learning about the Soundalyzer. I know I've enjoyed learning about the Arduino. It's amazing how such a small tool can be so powerful. And I've also learned how fun it is to take an everyday occurrence and analyze it. It's interesting how certain situations can compare with others when you take the time to study and break them down into their components. It's like there are so many answers to the questions we've never asked. This has been Randy Sturbins. Thanks for watching.